everyone. First of all, I would like to thank Protochips for organizing this flash talk. My name is Joséphine, and today I'll be talking about our work, which one part of it is published in Applied Catalysis, Environment and Energy, and another one is published in Molecules. This work is mainly about the use of environmental gas transmission electron microscopy for catalysis research. For a bit of context, as most of you know, catalysis has proven its importance on so many levels, whether in energy production industry, in the synthesis of organic and inorganic compounds. It has also promoted environmental protection and the higher standards of living. Most of these processes occur in what we call heterogeneous catalysis, where the reaction takes place on the interface between a solid catalyst and a gas or a liquid phase. Three case stages are included in this type of catalysis. First is the adsorption of reactant on the catalyst surface. The second stage is the reaction between the adsorbed molecules and leading to the formation of adsorbed products. And the final stage is the desorption, the detachment of the products from the catalyst surface. Now, the fact that all of these processes are occurring on the catalyst surface highlights the significance of this catalyst active surface area and the need to synthesize catalyst on a nanoscale to guarantee a high surface-to-volume ratio, enabling more reactants to reach the surface of the catalyst. So going from bulk to nanoparticles when maintaining a constant volume, the surface area varies inversely in this example for bulk nanospheres, for going from bulk spheres to nanoparticles. With a constant volume, the surface area varies inversely with the sphere's radius. Therefore, decreasing the radius leads to an increase in the surface-to-volume ratio. Now, researchers have dedicated a lot of their efforts to develop novel nanocatalysts with optimized morphologies and even higher active surface area to improve the catalyst efficiency. The hollow nanospheres are one of these novel catalysts. They resemble, as you can see here, to a capsule with an empty interior. I'm just going to try up. With an empty interior, this hollow cavity function as a confined space and act as engineered reactors. By confining reactors in this controlled environment, these nanoreactors promote efficient and selective chemical transformation. Now, this design with optimized morphology mainly offers a high surface area than the solid nanoparticles. It provides more active sites on the outer and on the inner shell of the for the catalytic reaction. Beside their low density, precious metals also synthesized in this morphology in hollow nanospheres allows also to save the material and reduce their cost. Now, considering the increased surface area, we have also to ask ourselves a question: how are these additional sites on the inner surface are actually accessible? We're going to revisit this matter later during my presentation. In our work, we've used the galvanic replacement reaction method to synthesize hollow nanospheres using cobalt nanoparticles as a template. So it's a replacement reaction that happens between cobalt nanoparticles and the platinum salt. Now, at this point, after synthesizing platinum-based hollow nanosphere as our material, the next question is: do these attractive characteristics of such systems endure when the catalyst is exposed to heat, pressure, and gases during a chemical reaction? The answer is no. During the chemical reaction, the activity of a catalyst is reduced over the course of the reaction. It's a loss in activity attributed to several transformations a catalyst undergo that can lead to its deactivation. One of these transformations is known by coking, This is the effect of the chemisorption of carbon on the catalyst surface. The catalyst, for example, deposits on the platinum nanoparticles, as you observe in this example, leads to the blocked active sites and eventually loss of platinum activity. A second transformation is known by the surface poisoning. This is when the strong chemisorption of reaction reagents or impurities that lead also to blocked active sites and eventually loss of activity of the catalyst. For example, carbon monoxide is widely known to poison platinum during heterogeneous catalysis owing to its strong donor acceptor binding ability. And finally, the sintering is the common deactivation mechanism for nanomaterials, leading to the growth of nanocrystals and reduction of the catalytic surface area. And this is the main concern that we've addressed during this work. As you can see in this image, the scale of these particles. So to observe them, we need a powerful technique with a high resolving power, such as the transmission electron microscope. So the core subject of this research is to investigate the behavior of platinum-based hollow nanospheres. Here we're interested mostly in the system, the hollow sphere morphology, and to study the behavior of this material during the carbon dioxide hydrogenation reaction, which is a model reaction we've chosen for hydrogenation reactions. This allows to gain fundamental insights into the catalytic performance under realistic operating environment. To achieve this, we've used in situ and Operando transmission electron microscopy techniques. This approach will allow us to have a real-time monitoring of both the morphological and compositional change in the nanospheres during the chemical reaction. We also focus on how temperature variations and gas composition can influence the overall thermal stability of platinum-based nanospheres. Using the galvanic replacement method, we've synthesized a first batch of hollow nanospheres by a manual addition of cobalt nanoparticles to a solution of platinum salt over an hour and a half. This synthesis led us to the formation of agglomerations of platinum-based nanospheres with a non-homogeneous morphologies. So, using the same concentrations, we've tried to another synthesis, and this time with a slower and more controlled addition of platinum salt to a solution of cobalt nanoparticles. We intended by this way to enable the platinum to effectively reduce the cobalt into solution and result more homogeneous particle morphology. And actually, it did work because we've obtained nanospheres with a more homogeneous morphology arranged in chains, as you can see here. So during this presentation, I will explain in details all the results regarding this set of nanospheres. And before concluding, I will go back to the first batch and focus only on the differences between these two batches, whereas in their initial state or their behavior under different atmospheres. So, as you saw, the synthesis resulted the formation of chains of nanospheres of an average length of 700 nanometer. This arrangement of nanosphere is caused by the addition of platinum salt to cobalt nanoparticles. So we had initially a high concentration of cobalt that promoted their agglomeration into chains, and the platinum replacing the cobalt printed the configuration of the chained cobalt nanoparticles. Now, from a morphological point of view, this high-resolution STEM image shows that the nanospheres forming the chain exhibit a discontinuous shell formed by randomly interconnected nanoparticles of about 2 nanometers in diameter, forming a shell with an average thickness of 5 nanometers. And also, for the chemical composition, since we've used cobalt as templates, we wanted to see if there is any residual cobalt content. And by collecting EDS spectra all over several regions, we've been able to determine an average cobalt content of about 7 atomic percent. These nanospheres present a central region that seemed to be empty or filled with a way less condensed matter. A higher magnification of the shell shows some kind of porosity within it. So we will dig deeper into this complex 3D morphology of the shell later using electron tomography. Before presenting you the results, I will explain briefly the principle of electron tomography. The first step involves the acquisition of a series of 2D micrographs at different tilt angles. These series are aligned. Then the volume is reconstructed using a proper algorithm. It all depends on the sample we're analyzing. And the last step is the segmentation that allows to visualize the 3D model of the sample. You see here the 3D model of three connected nanospheres we've analyzed, showing their complex morphology. And for a deeper analysis of the 3D morphology, this is the reconstructed volume. So here we have a plane, the XY plane, and with a variable Z. So we have a 2D plane, and we go deeper into the volume by varying the Z. From this reconstructed volume, we withdraw slices following different direction from the reconstructed volume. Now, these slices here offer a load of information that we wanted to know. First, it confirms that we have obtained hollow nanosphere. You can see the void. Second, the inner shell is not perfectly spherical. It presents facets. And these facets originate from the facetated cobalt templates. Third, and the most important, additionally to the confined space to take advantage of the inner surface offered by these nanosphere, it's important that we are sure of the accessibility of this surface. So you see here the open channels, that connects the outer space to the inner surface of the shell. Statistically, these channels are about 14 channels per nanospheres with an average diameter of 8 nanometers. That's an evident proof of the accessibility of the inner void by the gases during a chemical reaction. Now that we've wrapped up the pristine state of the platinum-based nanosphere system, I'll move to the core of the subject. How do these nanocatalysts react to temperature, pressure, and gas during a chemical reaction? The TEM, as we've said, offers a comprehensive view into the nanoscale catalyst down to the atomic resolution. But this is a static view of a static sample in an inert environment, since this technique operates under a high vacuum. So it lacks the real-time dynamic observation in real life conditions of the sample. A major development of the TEM, known by in situ TEM, allows to expose nanocatalysts to different control environments. Inside an environmental cell that is mounted on an in situ gas holder from protochips. The cell is formed by two silicon chips and mounted, as you see here, on a sample holder to form the environmental cell. This environmental cell possesses electron transparent windows on which the catalysts are deposited for TEM analysis. This cell can withhold up to 1 atmosphere of pressure and can be heated up to 1000 degrees. The inlet of this holder is connected to a gas manifold that allows us to control the gas composition and the pressure inside the holder, and the outlet is connected to a residual gas analyzer equipped with a mass spectrometer that allows for a simultaneous analysis of the reaction products while imaging the sample evolution. So using this setup, we are allowed to have a real-time observation of the catalyst, which is the hollow nanospheres in our case, under reaction conditions of a gas, temperature, and pressure, while simultaneously probing the reaction product, allowing us to observe the morphological evolution during the gas-solid interaction. Several phenomena, as you can see here, starting from the coalescence of the nanoparticles forming the shell until the collapse of the system, as you can see in this video. So, as a first study, we wanted to isolate the thermal effect of the nanocatalyst in an inert environment to investigate the fine evolution of the complex morphology. So we've conducted a thermal treatment under vacuum with a 20 to 50 degrees steps. The initial state of the particles is imaged at 120 degrees to eliminate all carbon-induced contaminations. Up to 280 degrees, I didn't observe any change in the nanoparticle size forming the shell. At 280 degrees, we observe the growth of some nanoparticles and disappearance of others. We track a change in the position of the nanospheres, of the nanoparticles on the periphery of the shell, an indication of their mobility. Starting 320 degrees, the central void diameter of the nanosphere starts decreasing gradually along with an increase in the shell thickness. Starting 400 degrees, the hollow microstructure starts collapsing with the maintenance of a rough surface. And finally, at 550 degrees, the majority of the hollow the hollow structure collapsed, and 25% of them preserved their hollow structure with a deformed void. So here we observe two major phenomena related to this thermal evolution. The first one is the growth of nanoparticles forming the shell. That's known by particles migration and coalescence mechanism. And the second one is the austral ripening mechanism, which is the growth of large nanoparticles at the expense of smaller ones. The second event is the collapse of the hollow structure, led by the crystal slip. The total and the partial collapse is directly linked to the shell thickness. Both of these phenomena affect the attractive characteristics of the nanoreactors in terms of the inner void and the shell morphology. Now, the next step is to monitor the behavior of these catalysts under hydrogen in atmosphere, which is the predominant gas in the CO2 hydrogenation reaction, the model reaction that we chose. So the initial state of these particles are probed initially under argon at 120 degrees to eliminate contaminations, and then a similar systematic heating was conducted after introducing the hydrogen gas, and the particles' morphologies was then monitored. The particles' mobility is evident starting 160 degrees, channels obvious at 120 degrees, maintained open up to 240 degrees, with the inner void, so the inner void remained accessible up until this temperature. At 320 degrees, we see a transformation from a discontinuous shell to a continuous one with more obvious facets previously seen in the 3D analysis. Finally, the total collapse and the gradual collapse of the hollow microstructure was observed at 450 degrees. The onset sintering temperature and the collapse temperature are lower than the one identified under vacuum. This behavior is driven, of course, by the effect of hydrogen gas on the surface reactivity of the particles. So hydrogen enhances the atomic mobility of the surface atoms, enhancing platinum atom surface self-diffusion. On the other hand, the presence of hydrogen caused an increase in atomic kinetic energy, overcoming the crystal slip potential barrier, so leading to an earlier collapse of the hollow structure compared to their collapse in the vacuum environment. The next step is to probe the particles' behavior under the actual CO2 hydrogenation reaction. So with the same strategy of thermal annealing, this is the initial state of the chains of nanospheres. After introducing carbon dioxide and hydrogen mixture and starting the heating process, migration of the particles are observed starting 180 degrees. The channels remained open and the inner surface remained accessible until 260 degrees, and a continuous shell was formed at 340 degrees with the collapse of the whole system at 500 degrees. By monitoring another region, evidence of a reduction in size of these two nanoparticles, as you see here, up until their disappearance, indicated the growth of other particles by Oswald ripening mechanism. The sintering onset temperature and the collapse temperature are higher than the one identified under pure hydrogen. This is probably the effect of 20% of carbon dioxide that reduced the surface atomic mobility, hindering both sintering and collapse. We said that we've monitored the reaction inside the microscope, and we've used a supposedly proper pressure and everything and all parameters. But did the reaction actually occur, and how can we confirm that? This question is answered by the residual gas analyzer positioned on the exit of the gas sample holder. So this analytical spectrum acquired at the gas cell outlet shows peaks corresponding to both reagents, hydrogen and carbon, and the product throughout the experiment. As you can see here, there are peaks corresponding to CO2, hydrogen, and their fragmentation, and also peaks corresponding to formic acid, methanol, and water that are also detected in this spectrum. Among these two possible pathways of carbon dioxide hydrogenation into methanol, this conversion over platinum catalyst took the formate pathway, indicated and evidenced by the presence and the detection of formic acid. Now, when is the reaction occurring throughout the experiment? A scan of the reaction possible product partial pressure as a function of time and temperature is conducted. The RGA allows us also to follow in real time the evolution of the partial pressure of these products as a function of time while controlling the temperature. The fluctuations seen here are related to a limitation of the RGA that has a threshold of pressure. Once it's reached, a safety measurement is triggered that pumps down the system. Another thing to say is this analysis of products, this analysis is only qualitative. So there's here at this point, we didn't have the possibility to have quantitative measurement of the product yield, for example. So, but what this spectrum shows is an increase in the formic acid signal starting 180 degrees. This means that the onset temperature for this product is 180 degrees. And for methanol, we see the increase of the signal starting 220 degrees, the onset reaction temperature for this product. All along the experiment, there is a continuous increase in the reaction products. This indicates also that the catalyst didn't undergo didn't deactivate by carbon monoxide poison, for example. As a final experiment, an isothermal reaction at the onset temperature at 180 degrees for 3 hours is conducted. We've conducted it to observe the morphological evolution of these particles as a function of temperature only. The nanoparticles' average evolution is measured as a function of time. There are two stages of growth. The first one is relatively fast. You have a growth from 3.5 nanometers up until 5 nanometers for the first hour. And then the second stage is a stable morphology that maintained that these particles maintained for over 2 hours. During these 3 hours, the reaction products are analyzed also simultaneously, and the reaction response in terms of their partial pressure is stable. So, taking, of course, into consideration the origin of this fluctuation, this stable response is also an indication that there is no catalyst deactivation by surface poisoning. Finalizing with this experiment, the study is conducted over this material. I will go back to the first particles from the first batch we've synthesized and present you the differences regarding their initial states and also their behavior in the 3 different atmospheres. Contrarily to the homogeneous morphology we've seen with that second batch of this change of nanospheres, the first batch presented 2 categories of nanosphere. The first one is a discontinuous shell formed by nanoparticles, and the other one is with a smaller diameter and a thin, smooth shell. The average diameter of these nanospheres is twice smaller than the nanospheres of the chains with comparable shell thickness and nanoparticles diameter. On the other hand, these particles have twice more elevated cobalt residual content. And the 3D analysis of the shell revealed, as I presented here, revealed a lower number of channels in the shell with smaller diameter. As for their behavior, the nanospheres of the first synthesis collapsed at lower temperature in the three different atmospheres, an indication of their lower thermal stability. And during the CO2 hydrogenation reaction with the applied condition, the nanoparticles forming the shell has grown into larger diameter nanoparticles than the ones seen in the second batch. This growth is probably linked to the higher cobalt content that promoted their growth. To conclude, these two batches of platinum hollow nanosphere were synthesized. We've succeeded to optimize a second batch in terms of morphology, accessibility of their inner surface area, and also these particles that also demonstrated relatively high stability even in highly reactive environments such as pure hydrogen. Information about the thermal evolution mechanism were also concluded. The synthesis The synthesized nanocatalysts were no subject to surface poisoning during the CO2 hydrogenation reaction chosen, and the reaction took, of course, the format pathway in both ways. So, thank you all for your attention, and I invite you to read more about this work and the two papers published. Thank you.